Well, welcome to Lesson 8 on direct variation. We're going to start this lesson talking about how a direct variation situation looks in words and how you can translate into a mathematical equation so that we can solve some problems. So you might see something that gives you two quantities in words, and it's going to say some quantity varies directly as another quantity. And we wrote this as A varies directly as B. In mathematical terms, what that's going to mean is A equals K times B, where K is called the constant of proportionality. And remember, a constant is just what it says. It is constant. It's some numerical value that you can calculate, and it always stays the same. So here's how it works. In this example, it says the number of teaspoons varies directly as the number of tablespoons. So there's your two statements. The number of teaspoons, and it tells you it varies directly. So those are key words, varies directly. Okay, so look for those as the number of tablespoons. So those are our two quantities that are varying that we care about. So I highlighted those to kind of show you what it is we're looking for. So it says if using 12 teaspoons is the same as using 4 tablespoons, how many tablespoons would be needed in a recipe calling for 6 teaspoons? Well, here's what we know to begin with. We know that I'm going to let little t be the number of teaspoons, and I probably should have defined that here. Little t is the number of teaspoons, okay? And then we're going to define capital T as a number of tablespoons. Okay, so just so we have our variables defined there. So this tells us, it says the number of teaspoons, little t, varies directly equals the number of tablespoons. They're equal to each other, but you have to multiply by a constant. So then the next sentence says, if using 12 teaspoons, so instead of t, little t, we want to put in a 12, and that's the same as using 4 tablespoons. So we're going to put in a 4 for the capital T. So 12 equals that constant times 4. Well, now we can solve that for k. Dividing both sides by 4, we get k is equal to 3. So the next step that you're always going to do, okay, this process remains the same. Once you solve for k, you want to go ahead and substitute it back in for k. So that gives us the equation t is equal to 3 times big T. Little t equals 3 times big T. This is our direct variation equation. Okay, so now we can answer the question, how many tablespoons would be needed? We're looking for big T in a recipe that has 6 teaspoons. So we know little t is 6. We want to find big T. So we're going to just substitute that in. So 6 equals 3 times T. Dividing both sides by 3, we end up with 2 tablespoons. Here's another example. It will follow the same process. It says when an item of clothing is on sale with a % discount, now look at these words. What varies directly? I'll highlight them again. The sale price varies directly as the original price. So that's a key piece of information there. If a shirt normally priced at $30 is on sale for $21. So here are our two items that are varying, okay? So we have a sale for 21 and we also have normally priced at 30, right? So we have two variables there. So what is the sale price? So we're looking for the sale price. I'll go ahead and highlight that again. What is the sale price when we have a normally priced at $40? So hopefully this isn't confusing. Hopefully this helps. So here we go. S is the sale price. I let P be the original price, and I wrote my equation. The sale price equals a constant times the original price. And we know that the sale price is 21 when the original price is 30 from the first highlighting set. So let's go ahead. We've written this equation. Let's substitute in what we know. The sale price is 21 when the original was 30. We can solve that then for k by dividing both sides by 30. So k is 21 over 30, and if you divide that out, you get 7/10. which in decimal is 0.7. So we always plug that back in for k and rewrite the equation. So S equals 0.7 times P. So now we can solve the second equation. It says, what is the sale price? We're looking for S if we plug in P equals 40. Plugging that in, we get S equals 0.7 times 40, and then multiplying that out, we end up with $28 is the sale price. Here's another example. It says the perimeter of a square varies directly as the length of the side. So perimeter varies directly as length of the side, right? If the perimeter is 20, so perimeter is 20, when the side length is 5, what is the perimeter when the side length is 9? So that's what we're looking for. Let's set up our equation. I said perimeter varies directly as the length, so P equals a constant times the length. Substitute in 20 for P, 5 for L, solve for K. We get K is equal to 4. Plug that back into our original equation. P equals 4 times L. Okay, just substituting that 4 for the letter K. Now we can solve the second problem. It says, what is the perimeter P when the side is 9? So we're going to plug in 9 for L. We get P equals 4 times 9, or 36. All right, here's another problem. It says the number of pages printed by a laser printer is directly proportional to the time the job takes. So let me highlight a few things, then I'm going to have you pause the video and do this one on your own. So the number of pages, it varies directly with the time. Okay? If the printer can print 21 pages in 2 minutes, so there's time, and here is pages. How many pages can it print in 5 minutes? So go ahead and pause the video, see if you can set the equations up, solve for K, and find the answer to how many pages it can print in 5 minutes. Alrighty, hope you gave that a try. Here we go. So P equals K times T, where P is the number of pages, T is time. Substituting in what we know, 21 pages in 2 minutes. Divide by 2 to solve for K. K is 10.5. Rewrite your equation. P equals 10.5 times T. And now we can plug in 5 for T. And we get P equals 10.5 times 5. And so multiplying that through, we get P equals 52.5 pages that can be printed in 5 minutes. All right, on this slide, we're looking for, it says the speed in meters per second of an object falling from rest in a vacuum is directly proportional to the time. So our two variables here, the speed varies directly with time, right? So those are our two variables. So here is time down here. Whoops. And then we have our speed column up here. So our task is, the table shows speed and time. We want to find out what x is. So what is the speed if the time is 7? It's the same process. Speed is equal to a constant times time. S equals K times T. S is speed, T is time. Pick one of these values. Doesn't matter which one. I'll show you both. So if we use the first set of values, the speed is 19.6 when time is 2. Divide both by 2 and K is 9.8. If you were to use these 2 points, you would get speed of 39.2 is K times 4. Dividing both sides by 4, notice that no matter which data point we use, we get the same constant. And so now we can put that constant back into our original equation here, the S equals K times T, but now K is 9.8. So now we can answer the question. We can plug in a value of 7 for T, and that gives us 68.6 for our speed, meters per second. So the last part of this problem says plot the 3 ordered pairs, and I gave you a graph in your notes, and I want you to plot those 3 ordered pairs and draw the line connecting them so that you can predict the speed at 10 seconds. I've done that for you. I went by 5s on my y-axis, that's the dependent variable. I put time as the x-axis and I went by 2's. And so here are my 3 data points. And projecting at 10 seconds, it looks like it would be probably about 100 is what I would predict. Okay, I would predict that that would be a 100 meters per second. And that's pretty close. If you put in 10 right here, you're going to get 98. So that's a pretty good prediction. And that'll do it for this video. We'll see you next time.